Hey guys, this is lecture video 11 of CSE2000Q2S Computer Science 2, taught by Lawrence Orijuela, and my name is Lawrence Orijuela. Today is November 13th, 2020, and we will be discussing searching and sorting. So if you look over at our tentative schedule, it's exactly the same as before. We're going as planned, and only one change has been made. You'll see that Lab 4 has been completely omitted from the course schedule. You're welcome. Yeah, so I mulled over it for a while, and I just decided to completely get rid of Lab 4 because I made all of these assignments over the summer, and I just told myself, yeah, this lab is way too similar to Act 10, where I discuss a bunch of... I discussed 3 different sorting algorithms with you, and I just wanted you to write a couple sentences explaining how each one works, but we actually go over that today in this video, and I don't really see the point in making you go over it twice. So yeah, I decided to completely remove Lab 4, and in the grade books, I'm going to give every student credit for Lab 4 as if it were an actual assignment. So there you go. So because it's November 13th today, you only have one assignment due tonight, and that's your Activity 9. Which, in my opinion, is the shortest lecture activity there was for this entire course. So please get that to me before midnight tonight. And next week, you're going to have your Lab 3 due. But this week, on November 13th, like right after you finish watching this lecture video, we're going to have a Zoom meeting for Lab 3. Where I will work with you guys to discuss like any errors that you might have with your Lab 3. But I'll discuss more about that later. So moving on. So this is a repeat of what I discussed before. So your Lab 3, your school database lab, watch this video. It's in Blackboard, and it's also on my YouTube channel. Please watch it after you finish lecture activities 6 through 8, and the link is here. And yeah, please get this to me before the due date on November 20th. Okay. And then here's another repeat of a slide from the last video. So on November 13th, which is actually today, if you're watching this video the day it's posted, we will be having a Zoom meeting for Lab 3 from noon to 12:50. And this is a repeat from what I said before. Lab 3 due date has been moved from November 13th to November 20th because we're going to take this Zoom meeting to resolve any errors that you might have with your person type.h, your student type.h, or your faculty type.h. And then December 4th is going to be the Zoom meeting for the final exam. The practice final has already been posted on Blackboard. And I will be posting the real final very, very soon. But during this meeting, you will, just like in the midterm, you will vote as a class which question is the hardest, and we will do it together as a class. Okay? And then, lastly, there's one other announcement that I've decided to make, and I think everyone would... I think most people will like this very much. So I've made a statement before that I wouldn't accept late work, but since we're winding down in these final weeks, I've decided that I will accept late work for reduced credits. Now, how much reduced credits is it going to be? Don't ask me yet because I don't know yet, but I have to be fair with all of the students who have been turning their work in time. But yes, I've decided I'll accept late work for reduced credit. So yes, just please turn it into me. Every single lecture activity, every single lab in this class, there is a video on Blackboard showing how to do it. So if you put in honest efforts and do a reasonable amount of work for the assignments in this class, I guarantee that you will pass this class. Okay? But anyways, that's enough of announcements. It's time to get down to lecture material. And so if you recall, we are actually discussing searching and sorting. I've decided to talk about the sorting part first, and we will discuss searching next week. Okay? So, anyways, what we're going to discuss now is sorting algorithms. Now, sorting algorithms has its special place in the realm of computer science, okay? Just because there's... When it comes to, like... for a computer science major, if you advance in your coursework, one of the classes that you're going to take is algorithm analysis. And that's the kind of course where you learn about all sorts of algorithms, how to analyze them, to see how efficient they are. So we talk about sorting algorithms a lot because they're perfect examples to apply our algorithm knowledge. Okay, so a sorting algorithm is used to rearrange a given array or a list of elements according to comparison to other elements. So let's say that we had an array of integers, okay? We would like to sort them so that they're in ascending order from least to greatest, right? We could, in theory, do the same with an array of characters instead, where we list them in alphabetical order. But for the most part, we're going to be talking about sorting algorithms that sort arrays, okay? Now, the reason why I'd like you to, I wanted to take time with this particular subject is because I have an important note down here. So, one day, if you're looking for a computer science job, important note, in coding interviews, potential employers will probably give you coding questions related to sorting algorithms. Okay, so if you were ever going to look for a job as a computer programmer one day, make sure you have a very good baseline knowledge on sorting algorithms and algorithm analysis. Okay, so sorting algorithms. There's actually a lot of sorting algorithms out there. There's lots of different sorting algorithms, and all of them try to accomplish the exact same task, which is sorting an array of numbers in ascending or descending order. Okay. Now, despite the fact that there's so many algorithms, many are more efficient than others, but we observe a range of them to develop a better understanding of algorithm analysis. Now, this picture here showing a long list of sorting algorithms. I can't take credit for this list. I took this list from geeksforgeeks.org/sorting algorithms. Now, despite the fact that there's so many, 3 of the classic sorting algorithms that people, especially interviewers, like to discuss the most is usually bubble sort, which is a fun one, quick sorts, and then a merge sort, which is considered the best sorting algorithm you can use. Okay? But before I go into algorithms, it's important that we take a moment to talk about something called Big O notation. Okay? Now, I'm not going to go super in-depth about what Big O notation is because you're going to learn this more if in advanced computer science courses, but it wouldn't hurt if we just took a brief moment to talk about it here. But you will see this one day, and you will really, really go into depth about Big O notation. Okay? So, Big O notation in computer science is a mathematical notation that describes the performance/complexity of an algorithm. Complexity is denoted in terms of the input size, which is n. Okay? Now, if you're ever calculating the Big O notation for a particular algorithm, there's two general rules that you need to follow. So the first rule is that constants are ignored. So I listed two examples here, right? So let's say that you calculated the big O for an algorithm to be 5 times the input size, so 5n. Here's the thing. We ignore constants. So this O of 5n would actually simplify to O of n, okay? Now, the reason why we ignore the 5, or any constant for that matter, is because we aren't concerned with how large n is. We're concerned about how quickly it grows when n increases, right? So if you took the graphs of like y equals 5x or y equals x, both of those are, both 5x and x, they're both increasing at the same rate. Well, not really, but well, what I'm trying to say is that they're both growing at the same speed in terms of n. So that's the reason why we ignore constants. The same is true for this other example that I listed. So let's say you analyze an algorithm and you calculated its O notation to be 1,000 n squared. We don't care about the 1,000, okay? We would reduce the big O of that algorithm to be n squared and ignore the 1,000, okay? And then the second rule for calculating the big O of an algorithm is that certain terms dominate others. So if you're trying to find the big O notation for a particular algorithm, what you should do is, out of all the terms listed, you should find the fastest growing n value, and that is your big O notation. You should ignore every other O notation there is. So if you look at this list here, this is these are sizes of big O notations. Like, these are the most common big O notations that you'll see for many algorithms, and they are listed in ascending order. So O of 1 is going to be your lowest O notation. This is the situation where it doesn't matter how large n is. The complexity of the algorithm is going to remain constant, okay? The next one following that is going to be log of n, which is going to, and after that is going to be O of n, O of n log n, O of n squared, O of n of 2 to the n, and then O of n factorial. So this one is constant. This one is increasing rapidly, and it's kind of like a range, you know? But don't worry too much if you don't quite understand what big O notation is. You will learn it in the future, and I have an example here. So let's say that you calculated the big O notation for a particular algorithm to be O of n squared plus O of log n. The reason why this reduces to just O of n squared is because you have one part of your algorithm increasing at a rate of n squared, and you have another part of your algorithm that's increasing at a rate of log n. Here's the thing. N squared is increasing much faster than log n. So as n gets bigger, eventually this part of the algorithm will dwarf this part of the algorithm. So we generally don't care about this. So like, maybe underline this part of your notes. Find the fastest growing n value. That is your big O notation. And that's what you do in this example. Because n squared is growing larger, we omit this and just say that the big O of our algorithm is just n squared. Okay? You're going to see how to calculate big O of particular examples of particular algorithms when we get into it. But if I go back a couple slides, so despite the fact that there's many sorting algorithms, I'll be introducing only 3 of them: bubble sort, quick sort, and merge sort. And reiterate from before, employers like to give questions in interviews regarding sorting algorithms, so make sure you pay good attention and take good notes, especially if you want to become a software engineer one day. Okay. So the very first algorithm we will discuss is the bubble sort algorithm. So how does bubble sort work? Well, bubble sort, just like all the other sorting algorithms, it takes an array of integers like this. Okay. Now, the way bubble sort works is that consecutive pairs of elements are looked at one at a time. So you start with 5, 1, then 1, 4, then 4, 2, and then 2, 8, like that. And if a pair of elements is in the wrong order, they will switch. Now, and the largest element will, quote unquote, bubble to the top of the list with each iteration. And the algorithm knows that it's finished if it does an entire iteration without performing any swaps. Okay. Now, I listed an example here, which uses the very integer array that you see right here. So I think I want to make this a little bigger so you can see it. Okay, I think that's good. Okay, so originally the array is 5, 1, 4, 2, 8. So as you can see, in bold is the pairs that's analyzed within each time. So the first pass indicates one iteration, second pass indicates the second iteration, and third pass indicates the third iteration. So in the first iteration, the pair 5, 1 is looked at first. Now, because 5 is greater than 1, the 5 and the 1 are out of place, so they will swap positions, right? And then the next pair that's analyzed, it's just shifting down the array. So the next pair that's analyzed is 5 and 4. So when 5 and 4 is analyzed, it'll see that 5 is greater than 4, so it'll swap it. And then after that, the next pair that's looked at is 5 and 2. Because 5 is greater than 2, 2 and the 5 will switch places. So now the array looks like this. And then lastly, it looks at the pair 5 and 8. Now, because 8 is greater than 5, they're actually in the same, they're actually in order already, so the algorithm does not swap them, okay? This indicates the first iteration. Now, in the second iteration, it looks at 1 and 4, right? Now, because they are already in the correct order, we don't change anything, so we look at the next pair. Now, 4 and 2. Because 4 is greater than 2, we would swap them. And then we look at the next pair, which is going to be 4 and 5. They're in the same order, so nothing changes. 5 and 8 is in the same order, so nothing changes. Okay? So at this point in time, the array is already sorted, but our algorithm doesn't know that it's completed. The algorithm needs to make one whole pass without any swap to see if it's sorted. So in the third iteration, it'll see 1, 2 is in order, 2, 4 is in order, 4, 5 is in order, 5 and 8 is in order. So in this iteration, because the algorithm made an entire pass without making any swaps, the algorithm knows that it's finished already. Okay. Now, it's a pretty simple sorting algorithm in like in terms of explaining it, but actually implementing the code to do it, that's actually a different story. But let me just put that here. So so over here, I actually have a snippet of the bubble sort algorithm. Well, this isn't the whole thing. I have I'm gonna show you the code later, but the reason why I'm showing this to you right now is because I want to demonstrate to you how to calculate the big O notation of the bubble sort algorithm. So as you can see, you have two nested for loops, okay? One is for I equals 0, I is less than n minus 1, I plus plus. The other one says j equals 0, j is less than n minus 1, minus I minus 1, j plus plus, okay? Now, the reason why it's n minus 1 iterations is because if you were... It's better if I do this. Because it's examining pairs at a time, the number of pairs it would look at is going to be this pair, then this pair, then this pair, then this pair. So because there's 5 items in this array, the number of times that the outer for loop iterates is going to be n minus 1. And then the number of times that the inner for loop iterates is also going to be n minus 1, okay? Because that's what we see in the algorithm, okay? So, therefore, the total number of processes that bubble sorts iterates is going to be O of n minus 1 times n minus 1. Because these for loops are nested into each other, we would multiply the number of times that they iterate together, okay? So, we get O, n minus 1, n minus 1. If we use algebra, we will get n squared minus 2n plus 1. And because the O distributes, we can divide this into O of n squared plus O of 2n plus O of 1. Now, if you go back to our general rules over here, remember, certain terms dominate others. Find the fastest growing n value. That's your big O notation. So because this O of n squared is increasing faster than the other two terms, eventually when n gets large enough, this part of the algorithm is going to grow so large that it'll completely dwarf these two other parts of the algorithm. So we would ignore them. So our resulting big O of our bubble sort algorithm is going to be O of n squared. And I feel like this is important to mention too. This is the average case. Well, eventually, if you learn more about big O notation, we're going to start talking about worst case, average case, and best case. But generally speaking, we will be talking about the average case, okay? So it's finally time to do our lecture activity. So we will go to Blackboard, look for the tab labeled Sorting Algorithms, open the text file named Bubble Sorts, copy paste the code to your IDE, run, and take a screenshot. Okay? So here's what I'd like you to do. I'm going to open Blackboard on my other monitor here. Well, actually, first, let's open Visual Studio. Click Create New Project, empty C++ project. Go to the place where you normally save your lecture activities. For me, it's going to be here. Now, because this lecture activity has 3 parts, what I'd like you to do is call this Lecture Activity 10A. Okay. Click Create. Go to Source Files, hover over Add, click New Item. For your main.cpp, call this main a.cpp because we're going to make 3 of these, okay? Click Add. Now, if you actually went to Blackboard, like I'm here on Blackboard right now, you'll find a tab called Sorting Algorithms. Click that. And here are all the code for the 3 different algorithms that we're going to be reviewing, okay? So what I'd like you to do is click the one called Bubble Sorts. Now, I already wrote the code for you, Now, the reason why I'm not asking you to write this code from scratch is because, well, you'll never be asked to, because here's the thing. All three of these algorithms here, they're classic algorithms. So there's no need to write it again. Like, if you Google it, you'll probably find the code online, because all of this code is heavily used already. And for me to ask you to write the code for this, it's like asking you to reinvent the wheel, right? So in a coding interview, you'll never be asked to write an algorithm from scratch. But you will be asked to analyze it and understand it and answer any questions regarding this algorithm to show your basic understanding, okay? So in order to show this to you, I would like you to copy paste this. Like that. Go back to Visual Studio, paste it here, save it, and let's run it, okay? So this is our integer array before actually sorting, okay? Now, we had the integers 0 through 9, but they were scrambled, okay? This here just calculates the size of the array, and this is printing the array before sorting. Here's our sorting algorithm here, and this is our array after sorting, okay? Now, if you wanted to see how this code is working, well, don't worry so much if you don't quite understand how this code works, but really, there's only the bubble sort algorithm is comprised of only two functions, okay? One is the bubble sort algorithm, and the other one is the swap function that we use, okay? So in the bubble sort algorithm, we see the two for loops, right? So where we look at pairs of elements one at a time, and then we look at the ith element and the jth element, and we compare them to each other, and if j is greater than j plus 1, we will swap the two. And as you can see with these, the address of operators here, because we need to pass it by reference, because if we weren't passing by reference, we'd be editing a copies of the elements instead of the actual elements, okay? But anyways, if you want, take a moment to analyze this code, see how it works, but basically that's all you need to do for lecture activity 10A. Okay, so I think we can move on to the next algorithm, which is going to be quick sorts. Okay, now quick sorts is, as I said before, all of these sorting algorithms, they're trying to accomplish the same thing, right? The only thing that's different is the method by which they try to do it. Now, let's talk about quicksort. Quicksort is a recursive algorithm. Hey, we learned recursion in the previous week, right? So, because it's recursive, it calls itself repeatedly. And by doing so, it takes a large problem that by nature would be very difficult to solve, but it breaks it down to smaller and more manageable problems with each iteration. And well, last week we talked all about recursion. You probably already know how powerful recursion is, right? So I'm not gonna go super into depth into it, but anyways, how does quicksort work? Okay, so the way it works is that a number is randomly chosen from the array. It could be well, it's systematically random, but this number that's chosen, it could be the first element. Sometimes it's a last, sometimes it's a middle element. It doesn't really matter. But whatever number we choose is called the pivot. Okay? All numbers less than the pivot are moved to the left of the pivot. And then all numbers greater than the pivot are moved to the right of the pivot. Okay? The quicksort algorithm is then applied to the left and the right halves of the remaining array. So we can see quicksort happening to this example here. So we have an array of 7 elements. 5, 8, 1, 3, 7, 9, 2. Like that. Now, this particular quicksort algorithm, it takes the first element and makes it the pivot. But it doesn't have to be the first element. It could be the last or the middle. It doesn't matter because the result is always the same. So what happens is it takes 5, moves it to the middle, and then takes each remaining element, takes all the elements that are lower than 5 and puts it to the left. So 1, 3, and 2 are all lower than 5. So they are moved to the left. See? And then the remaining elements, 8, 7, and 9, are moved to the right. Okay? So with this pivot here, the pivot is already in the correct location it needs to be. And all of the remaining elements, they're in the correct position relative to where the pivot is. They're just in the wrong order. So the way we would continue this further is that we would apply the quicksort algorithm to both halves of the remaining array. So we would treat 1, 3, 2 and 8, 7, 9 as 2 different arrays. And we continue the same trend as before because this is a recursive algorithm, okay? It's calling itself repeatedly. So for this array, for this sub-array here, 1, 3, 2, 1 is selected as the pivot, and then the remaining elements, 3 and 2, because they're greater than 1, they are placed to the right, okay? And we can apply the recursive algorithm again, quicksort on the left and right. Because on the left there's no algorithm, this would be considered the base case and we would return. But over here on the right, we have elements 3 and 2, which might not necessarily be in the correct order. So we take the first element again, which is going to be 3, and we take the remaining elements. In this situation, there's only 1, and that's element 2. We put that to the left of the 3, okay? And then when we're ready to, because this array was broken down to just one singular element, that's the base case that we would return. So this 2 and this 3 would come back together to make a sub array of 2 and 3, and then it unites with the pivots and the left array, which doesn't exist, right? Because there's nothing there, and it would unite to make the sub array 1, 2, 3. And then as for the right side here, 8 becomes the pivot of the sub array. 7 and 9 is put to the left and the right because 7 is lower and 9 is greater. These elements, because they're singular elements now, this is the base case, and we put them back together, 7, 8, 9, and then this subarray and this subarray come back together with the pivot, which is 5, and make the whole array but sorted again. So 1, 2, 3, 5, 7, 8, 9. Now, if you were asked to write a sorting algorithm, this probably isn't a very intuitive way that you would sort an array of integers, but quicksort is actually a very commonly used sorting algorithm, and it's actually more efficient than the bubble sort algorithm that we were looking at before. If you recall, if I go back a little bit, the big O of bubble sort is O(n) squared. Okay, so this means that as as the input size n increases, the number of processes that's required to perform bubble sort is going to be n squared, which increases very quickly, and that's not very good. If we calculate the big O of quicksort, what we're going to find is that quicksort has a lower big O notation than bubble sort, meaning that it's a more efficient sorting algorithm than bubble sort is. Okay. Now, in order for me to explain why quicksort is more efficient than bubble sort, I need to first draw your attention to this diagram here. Okay. So over here I have some code, and over here I have this diagram, right? So without looking at the code, you kind of already know how quicksort works. So the array is being split in half every time. So in this diagram here, we had an array of 8 elements. They're being split into 4 and 4, right? Well, excluding the pivot, but we can disregard that for now, okay? These elements of 4, they're being split into arrays of 2 and 2. And then these arrays of size 2, they're being split into, arrays of size 1, as you can see. So, over here in this box here, we have the quicksort algorithm. It consists of 2 parts. One is a part where this partition user-defined function is called. The way that partition works is that it selects a pivot, which is a random number selected from the array, and it takes all of the elements that are lower than the pivot and puts them in an array that's to the left, and takes all of the numbers that are higher than the pivot and puts them to an array on the right. Okay. Now, so that's the first part of the quicksort algorithm. The second part of the quicksort algorithm is these 2 recursive calls. So you see that this is the quicksort algorithm, right? It calls itself twice, and that's why it's a recursive algorithm. Okay. It's going to each call of quicksort is going to accept 3 variables. One is going to be the pivot. The other is going to be the low end of the array, the high end of the array, the pivot, low end of the array, high end of the array. Okay. So with that in mind, we can actually begin calculating the big O notation for quicksort now. Okay. So going over here. So as I said before, the quicksort algorithm consists of 2 parts. One is the partition function, and the other one is the 2 quicksort iterative calls. Okay. Now, if you look at the previous slide, because we have a for loop here that's completely dependent on the size of the array, we say that the partition part of the function iterates n times, where n is the input size, right? Now, the 2 quicksort iterative calls divides the array in half each time, right? Now, I mentioned this before, like recursive definitions require 2 things. One is the base case, one is the general case. In this particular example of quicksort, the general case is we split the array into 2, but the base case is when the array cannot be split anymore. In other words, it's just one element and it's not divisible anymore. That's the base case, and that's when we return, right? Now, it's because of this that we have to be aware about how many layers there are in this diagram. So, in order to find the number of times that the array splits, we have to do a little bit of math. So, the number of times in which the 2 quicksort iterative calls iterate is the number k, where k is equal to n divided by 2 to the power of k, equals 1. And that makes sense because we're cutting the size of this array in half each time, and we have to find the number of times we're dividing by 2, where the size of the array after dividing it by 2 that many times is going to be equal to 1, because that's when we return. So if we want to find the value of k, it's very simple. We just need to do a little bit of math. So multiplying both sides by 2k, we get n equals 2 to the k. And solving for k, we get k equals log n base 2. But here's the thing. Because we don't care about constants, if you go back to this rule here, yeah, constants are ignored. Because of that, the number of times in which the two quicksort's iterative calls iterate is going to be log of n, where n is the input size, okay? So we have n, where the partition function is called, and we have log n, where the two quicksort iterative calls are dividing this array each time. The partition function is occurring each time we do an iterative call, okay? So as a result, because partition is iterating n times, quicksort is iterating log n times, the big O of quicksort is going to be O n log n, okay? N log n. If you wanted to compare this to the bubble sort algorithm, its big O is n squared. And if you actually went back to this chart here, n log n is smaller than n squared. So because of this, we say that quicksort is more efficient than bubble sort, because its big O notation is smaller than that of bubble sort. And more or less, this is the reason why we study sorting algorithms so much, because it's a good example to talk about algorithm analysis. So far we discussed bubble sorts and quicksorts, but you probably want to see quicksort in action. Now, I went through the courtesy of posting all of the code for the sorting algorithms on Blackboard for you, so you can copy, paste it, and run it. So we are on lecture activity 10b. Please follow these steps. Go to Blackboard, go to tab labeled sorting algorithms, which we already have. Open the text file named quicksort, copy paste the code to your IDE, run it, and take a screenshot. Okay. Now, this is 10b, right? We did 10a a while ago. Here's what I'd like you to do. Don't close this, actually. Just minimize it and open a brand new Visual Studio. And let's make a new program. We will call this lecture activity 10, and because this is the second part, we're going to call it 10b. Okay? Create. Okay. Put this right here. Source files, click add new item. This main.cpp, call it main b.cpp. Click add. Perfect. Now let's go back to Blackboard, and you can find the quicksorts algorithm right here. So click this. Here's the code. Copy paste this into your IDE. There we go. Now, save that. Now, as you can see, this array here, it's the exact same array of 10 integers in the exact same scrambled order that was in the previous code. Like I said before, every sorting algorithm is trying to accomplish the same thing, right? So this is the array before sorting. Here's our sorting algorithm, which is in the form of a user-defined function, and here's our array after sorting. Okay. Now, don't worry too much if you don't understand how this code works. Like I said before, you'll never be asked to create a sorting algorithm from scratch. But if we looked at this, we can kind of see what's going on. So the quicksort algorithm is down here. It comprises of two parts. One is the partition where we choose our pivots and divide the array into two parts, the high and the low. And here are our two quicksort recursive calls, where we perform the quicksort algorithm on the two divided arrays. And we will continue doing this over and over again until it cannot be done anymore. So here in this particular quicksort algorithm, it actually selects the highest number of the array to be the pivot. But like I said before, it doesn't really matter what you choose as your pivot. And then it does the swap if there's an element that's lower or higher than your pivot. Okay? But if you wanted to see this working, we can run this. And we can see that the array is sorted. Okay? Now, if you have... I'm going to dock lecture activity 10b over here. And I'll put 10a over here. So, let me do this. Now, I'm not going to ask you to do this, but I'm just saying that if you did do this, if you put a breakpoint where the bubble sort algorithm is called, and a breakpoint where the quicksort algorithm is called, and if you try to debug both of them one by one, generally speaking, you should find that the quicksort algorithm, which is on the right side here, will go through less processes than the bubble sort algorithm, which is over here. Now, efficiency is very important, especially in computer science. And this is the reason why we discuss about algorithm analysis a lot. But anyways, I'm actually not going to debug it. If you wanted to, you can do it on your own time. But anyways, let's minimize these for now. So the very last algorithm that I'd like to show to you is merge sorts. Right? So these two Visual Studios here, keep them for now. And the last algorithm we're going to discuss is going to be merge sorts. Now, to reiterate from before, there's a lot of different sorting algorithms out there, but out of all of them, merge sort is generally agreed upon to be the most efficient. Even though, if you look at the way that merge sort performs, you might not think it to be, but it is. Okay? So, merge sorts, like quicksort, is a recursive algorithm. Okay? It calls itself repeatedly, taking a large problem and breaking it down to more manageable versions of the problem. Okay? Now, how does merge sort work? Well, it's very similar to quicksort in the respect that the array is being split in half every time until the array cannot be split anymore. But the difference between quicksort and merge sort is what happens when we're like recombining the divided arrays. So eventually, as we break this array down into its individual parts, what happens next is that we start reassembling the array, but we put them in ascending order. Okay, so at this point here, we've completely broken down the array, and we're looking at 38 and 27. We consider these like two different arrays of size 1. Okay. Now, the way that the new array is reassembled is that it looks at both arrays. It looks at the first element. It selects the lowest between the two first elements, and then it takes the lowest element and makes it the lowest element of the combined array. So it takes 27 first, and then after that, only 38 is left, so 38 is added next. Same thing goes with 43 and 3, 9 and 82, and 10. Okay? Now, when these two arrays are combining, the way it works is that it looks at each subarray, looks at the first element, tries to determine which one is lower, and then puts that one first. So after 3 goes there, the new first element is going to be 27 and 43. But because 27 is lower than 43, it'll add 27 next. Then we're left with 38 and 43. 38 is lower than 43, so it'll add 38 next. Then 43. A similar thing happens to the other half here. So we got 9 and 10. So because 9 is lower than 10, we would add 9 first. So we're left with 82 and 10. Because 10 is lower than 82, we add 10, then 82. Then these two subarrays are examined and then merged again. And this is where the merge of merge sorts comes from. This is the namesake per se. Now, the reason why that this is the most efficient algorithm is because it's combining. It has the benefit of recursion, okay? But when it comes to reassembling the array, we're not looking at the entire array exactly. We're just only looking at the first element of the subarrays. And we're taking each first element and making new subarrays from it. And that's why it's more efficient than the other two sorting algorithms we looked at, because for these subarrays, we're not iterating through every element. We're only looking at the first element each time. Okay? So, with that, we can probably try to calculate the big O of merge sort now. So, merge sort consists of two different parts, the same way quick sort consisted of two different parts. So the first part is going to be this merge function, which is listed here. And then two recursive calls of merge sort, okay? So because merge sort is recursive, it'll call itself repeatedly. And then when it comes to this merge function here, this is the code. Even though it looks long, it's actually simpler than the code of the previous two sorting algorithms, because here's the thing. We're only looking at the first element of each subarray. And that's why it's more efficient. So, moving on to the next slide. If you wanted to calculate the big O of merge sorts, you only need to keep two things in mind. One, the process of merging the two arrays iterates n times. This n is being performed by the merge function here. And then the two recursive merge sort calls iterates log n times. Now, you might notice that the number of layers here for merge sort, it's actually twice the number of layers of quick sort if I go back. So quick sort has for an array of size 8, there's 4 layers. But for an array of size 8, well, I know this isn't 8, but it's 7, but it's close enough. For an array of size 8, it's twice the number of layers almost. So, because of that, the two recursive merge sort calls iterate 2 log n times. You might think that's makes it more inefficient, but it doesn't, because here's the thing. We don't care about constants. So instead of being 2 log n, it's just log n. So because this n is occurring log n number of times, the big O of merge sort is going to be these two values multiplied by each other. So it's going to be O of n log n. Okay? Now, merge sort is like I said before, it's arguably the most powerful sorting algorithm there is. So we can demonstrate it in the last part of the lecture activity, which is lecture activity 10C. Go to Blackboard, go to the tab labeled sorting algorithms, open the text file named merge sort, copy paste the code to your IDE, run and take a screenshot. Okay? And this is actually the last part of the lecture activity. So open a brand new Visual Studio. Create a new project, empty project. Let's call this lecture activity 10C. Add a main.cpp. Let's call it main c.cpp because this is part C. And then go back to Blackboard and click on merge sort.txt. Copy paste all of this and you will see merge sort in action. Yeah. Now, to tell you the truth, all this code for the sorting algorithms, I actually copy pasted them from online. Because like I said, you'll never be asked to write these algorithms from scratch. It's all online. So hey, if you wanted to learn more about sorting algorithms, one thing that you could do, like on your own time, you could go to geeksforgeeks.org/sorting algorithms, and you will find a whole section showing you all sorts of different sorting algorithms, like all these. Okay. Now, you might not need to learn like all of these sorting algorithms, but it would be good practice if you maybe looked at some of them. But yeah, going back to the lecture activity, we can see the way that merge sort works here. These are the two recursive calls. This is the merge function being called. And we can see it in action. This is the same array of size 10 in the same scrambled order in the previous two examples. And if we run it, array before sorting does it, and then after sorting with merge sort, we get this. Okay? So, basically, this is the very last lecture activity of the entire course. Okay? Now, even though we have, I have one more lecture regarding the searching part of searching and sorting. It's not going to have a lecture activity, but I'll be posting a video anyways for your learning purposes. But the only thing that I want you to turn in terms of Act 10 is these three programs that we wrote. Okay? So when you're ready to turn this in, you need to do a couple things actually. So let me go back here. So as always, you know how to turn this in, but for this particular lecture activity, I need 6 items from you. The screenshots and the CPP file of the 3 different sorting algorithms that we discussed today. So send this to me. Call this CSE2000Q2S, last name, first name, Act 10. This is the very last lecture activity that you're going to turn in. Okay? So, run 10A, which is going to be the bubble sort algorithm. Take a screenshot of this. put it in the body. Close this. Go to 10. Well, close 10A right now. Then go to 10B, which discusses the quicksort algorithm. Run it once more. Get a screenshot. Paste this in the body of your email. I don't really care the order in which you put these screenshots. I can look at it and figure it out. And then lastly, close 10B, open 10C. This is merge sort. Run it once more. Once again, take a screenshot. And then put this in the body of the email. And then lastly, attach the 3 separate CPP files to me. Okay? So, go over here. Find the place where you save your lecture activities. So I have 10A, 10B, and 10C. Open each one by one. Go to the project folder. Select your main a.cpp. That's actually why I asked you to name it main A, main B, main C. And then attach, go back, go to lecture activity 10B, attach main B.cpp. Okay. And then lastly, go back and select main C.cpp. And once you send this to me, you have officially sent me your last lecture activity. Okay? So yeah. Now, like I said before, even though we have 2 weeks of searching and sorting, this next part, I'm not gonna have like an activity for you to turn in, because when we're talking about searching and sorting, we're actually kind of dipping into material that you would see when you take CSE 2020. And that's kind of beyond the scope of this class. So, so next week is going to be your last lecture video. And sometime in the weeks after that, I will be posting the video showing you how to solve your practice final. And but yeah, that's basically it. We are almost completely done with this course. So congratulations. I hope to see you in the Zoom meeting later today from 12 to 12:50. I'll be sending an email in regards to that. Please join it if you're experiencing difficulty with your Lab 3. But yeah, that's basically it for this lecture video. And I will probably see you soon. Goodbye.